7 decades of serious scientific work. 0 answers. That is not a rhetorical setup. That is the actual state of the Fermi Paradox in the year 2025. Enrico Fermi asked one question at lunch in the summer of 1950, and no one, not a single physicist, astrobiologist, or mathematician since, has been able to close it. The question was, where is everybody? Fermi was eating in the Los Alamos cafeteria in New Mexico at a table with Edward Teller, Herbert York, and Emil Konopinski. They had been talking about a cartoon in the New Yorker, flying saucers, the usual joke, and then the conversation drifted the way lunch conversations do, and Fermi said something that stopped the table. He had done a rough calculation in his head. The galaxy is old enough, the distances are enormous but crossable over geological time. Even at a fraction of the speed of light, a civilization that started a few million years before us could have colonized every star system in the Milky Way by now. And yet, he looked at the others and said, "Where is everybody?" York remembered it for the rest of his life, not because the question was new, people had wondered about other life in the universe for centuries, but because of the precision underneath it. Fermi wasn't asking philosophically. He was pointing at a specific, measurable gap between what the math predicted and what the sky showed. The math said, they should be here. The sky said, they are not. That gap has a name now, and it is never closed. I keep the Fermi Paradox in a specific category in my mind, not as a puzzle that needs more data, but as a diagnostic. It tells us something about the structure of reality, not just about the frequency of life. The question is not, are we alone? The question is why the universe, which is 400 times older than Earth and contains roughly 200 billion galaxies, each containing hundreds of billions of stars, has produced, as far as we can detect, exactly one civilization capable of asking the question. That asymmetry is the thing. That's what Fermi saw at lunch. The most widely discussed resolution is called the Great Filter. Robin Hanson, an economist at George Mason University, formalized it in 1998. He was sitting with a spreadsheet of probabilities, working through what it would take for a civilization to cross each developmental threshold, from simple chemistry to complex cells, from cells to multicellular life, from multicellular life to intelligence, from intelligence to space travel. And he noticed something. If even one of those thresholds is catastrophically unlikely, something like a 1 in a trillion chance rather than a 1 in 1,000 chance, it would explain the silence completely. You don't need aliens to be rare everywhere. You just need one step to be nearly impossible, and the output of the whole pipeline collapses to near zero. He called it the Great Filter, and then he pointed out the thing that makes it genuinely disturbing. Either the filter is behind us or it is ahead of us. If it's behind us, if the nearly impossible step was something in our past, like the origin of eukaryotic cells or the emergence of sexual reproduction, then we got lucky. We crossed the threshold that almost nothing else crosses. The silence is explained. We are an outlier, and the universe is otherwise empty of complex life. That is frightening in its own way, but it is survivable knowledge. If the filter is ahead of us, then every civilization that reaches our level eventually hits something that destroys it. Nuclear weapons, engineered pathogens, climate collapse, a technology we haven't invented yet whose downside is extinction. The silence is not because life is rare, it's because civilizations consistently fail to survive themselves, and we are approaching whatever that thing is. Here is where the Great Filter breaks as an answer. It doesn't actually resolve the paradox, it reframes it. It says the silence is explained by a bottleneck, but it cannot tell you where the bottleneck is, and the location of the bottleneck is the entire question. If you cannot specify whether the filter is behind or ahead of us, you have not answered anything. You have given the silence a name and called it a solution. The paleontologist Peter Ward and the astronomer Joe Kirschvink spent years cataloging the extinctions in Earth's deep past, the Cambrian explosion, the Permian catastrophe, the long stretches where life repeatedly nearly ended. Their argument was not that the filter is behind us. Their argument was that Earth itself is a freak, the right distance from a stable star with a magnetic field, with plate tectonics, with a moon large enough to stabilize the axial tilt. They called it the rare Earth hypothesis. They published in 2000. The book is still in print. It is also not a resolution. It just pushes the probability down further and leaves the paradox intact. The second class of resolution is simpler, and for a while, it sounds almost comforting. Maybe the distances are just too large. Maybe interstellar travel is not physically possible in any practical sense, not because of the physics, but because of the timescales. Even at 1% of the speed of light, reaching the nearest star system takes over 400 years. Reaching the other side of the galaxy takes millions. No civilization maintains a coherent project over millions of years. The Romans couldn't maintain an empire for 1,000. So maybe the galaxy is full of civilizations, all of them trapped inside their own little bubble of reachable space, all of them broadcasting into a void that is simply too large to cross. This is the isolation hypothesis. It was articulated seriously by the physicist Sebastian von Herner in the 1961 paper, The Search for Signals from Other Civilizations. He did the math on signal propagation and concluded that even radio signals, which travel at the speed of light, fade into background noise within a few hundred light years. We have been broadcasting for about a century. Our radiosphere is 200 light years in diameter. The Milky Way is 100,000 light years across. We have announced ourselves to a sphere containing roughly 10,000 star systems out of 400 billion. We are not quiet. We are just very small. That part holds. The problem is the other direction. If distances explain why they haven't come here, they don't explain why we haven't detected anything. A civilization broadcasting for 100,000 years, which is nothing on geological timescales, would fill the galaxy with signals. A civilization that started sending self-replicating probes at even a fraction of the speed of light would have covered the galaxy in a few million years. The distances argument explains the absence of visitors. It does not explain the absence of signals, artifacts, or any trace of directed activity in the entire observable universe. Jill Tarter spent 30 years at the Search for Extraterrestrial Intelligence Institute in Mountain View, California, leading the most systematic attempt to answer Fermi's question through observation. She sat in control rooms watching spectrographs, listening to data from radio telescope arrays, running pattern recognition software over terabytes of sky noise. She made a point she repeated often in interviews. The total volume of cosmic data we have carefully examined for signs of intelligence is roughly equivalent to searching for fish by scanning a single glass of ocean water. We have not found fish. That does not mean the ocean is empty. The absence of a signal in our current search radius is not the same as the absence of a signal. It is a data point, not a conclusion. But here is the uncomfortable arithmetic. The glass of ocean water is getting larger every year. We have examined more of the sky in the last decade than in all previous decades combined. The silence persists. At some point, we don't know when, the failure to detect becomes statistically meaningful rather than just statistically incomplete. We are not there yet, but the water in the glass is rising. The third resolution is the one that has entered popular culture most dramatically, partly because a Chinese science fiction writer named Liu Cixin articulated it with a precision that most scientific papers don't reach. His argument in the novel that describes it is this: the universe is a dark forest. Every civilization is a hunter, moving silently through the trees. Broadcasting your location is death. Every civilization that emits signals gets destroyed by civilizations that detect the signal and fire first, not out of cruelty, but out of rational risk assessment. You cannot know the intentions of the civilization you detected. The cost of assuming they are benign and being wrong is extinction. The cost of firing first is only the resources spent. Under that logic, every civilization that survives long enough to be capable of interstellar warfare has already learned to be silent, and every civilization that announces itself has already been eliminated. The dark forest hypothesis is logically coherent. It is also, on examination, incomplete in a specific way. It requires that all civilizations independently arrive at the same strategic calculus and maintain it indefinitely. It requires that there are no exceptions, no civilization in the entire galaxy that is either too primitive to understand the game or too powerful to care about being detected. It requires that the galaxy has been in a state of mutual deterrence long enough to produce total silence, which means the period of initial naive broadcasting was short enough that we happened to start listening right after it ended. The timing problem is severe, and it requires that the physics of weapons capable of eliminating a civilization from across interstellar distances actually exist, which we currently have no evidence for. The zoo hypothesis has the same structure with different emotional content. Perhaps advanced civilizations are watching us, but have agreed not to interfere, the way a nature reserve enforces a no-contact policy with uncontacted peoples. We are the exhibit. The fence is invisible. They are there. We just cannot see them. The zoo hypothesis fails the same way. It requires all spacefaring civilizations to have agreed on and maintained the same policy with zero defectors. Any one civilization breaking protocol would have announced the rest. Either they are extraordinarily disciplined, or the zoo requires a level of coordination across unrelated species that has no analogy in any system we know. You can believe it. It is not ruled out. But it is not a resolution. It is a speculation dressed as one. In August of 1977, an astronomer named Jerry Amon was sitting at his desk in Columbus, Ohio, reviewing paper printouts from the Big Ear radio telescope at Ohio State University. The telescope scanned the sky automatically. Amon checked the output by hand. He was looking at a column of numbers representing signal strength on a scale from 0 to 9, then letters continuing the scale, A representing 10, B representing 11, and so on. Most of the printout was low numbers, noise, background, nothing. Then he found a sequence, 6, E, Q, U, J, 5. The peak, U, represented a signal strength of 30, nearly 30 times the background noise. It lasted exactly 72 seconds, which was exactly how long a signal from a fixed point in space would appear as the Earth's rotation swept the telescope's beam across it. It came from the direction of Sagittarius. It was at the right frequency, the hydrogen line, 1.42 gigahertz, which physicists had long predicted would be the natural broadcast frequency for an intelligent civilization trying to be detected because it is universal and distinctive. Amon circled the sequence in red pen and wrote a single word in the margin. Wow. 48 years later, the wow signal has never been repeated. No instrument has detected it again from the same coordinates. We do not know what it was. The astronomer Antonio Paris proposed in 2016 that it might have been a hydrogen cloud trailing a comet passing through the field. Other astronomers have contested the analysis. The question is open. What is certain is that we detected once a signal with all the properties we would predict from an extraterrestrial broadcast, and then it was gone, and we have heard nothing like it since. This is not nothing, but it is also not an answer. It is one data point that is either a natural phenomenon or the most significant detection in human history, and we cannot tell which. The fifth and sixth resolutions compress under scrutiny into a single problem. The simulation hypothesis says we might be running inside a computational process, and the universe appears empty because populating the simulation with active extraterrestrial civilizations would be computationally expensive and unnecessary for whatever the simulation is designed to test. The rare Earth hypothesis says complex life requires such a specific combination of planetary conditions that it almost never arises, and so the universe is genuinely nearly empty. These look like opposites, One says we are inside a designed system, the other says we are the result of improbable natural processes, but they share a structure. In both cases, the answer to "where is everybody" is "there isn't anybody." And here is why we are the exception. One invokes a designer, one invokes statistics. Both say the silence is real, and we are the anomaly. The problem with both is that neither is testable in the specific way we would need to use them as answers to the Fermi paradox. The simulation hypothesis has no observational prediction that distinguishes it from a non-simulation. The rare Earth hypothesis is a probability argument that depends on parameters: the frequency of stable solar systems, the frequency of large moons, the frequency of plate tectonics, that we do not currently know. We are discovering new planetary systems every year. The data keeps changing. The argument keeps being revised. It is not wrong. It is not right. It is incomplete in a foundational way. The thing I find myself returning to, not as wonder, but as a specific intellectual discomfort, is that every resolution to the Fermi paradox requires assuming something we cannot verify. The great filter requires assuming a bottleneck we cannot locate. The distances argument requires assuming our search is too limited to be meaningful. The dark forest requires assuming a universal strategic calculus. The zoo requires assuming universal cooperation. The simulation requires assuming we are inside one. The rare Earth requires assuming our probability estimates are roughly correct. Every resolution is a theory built on an assumption. None of them is built on a detection. The seventh resolution is the one that gets the least attention because it requires dismantling the question rather than answering it. Frank Drake, not Fermi, but Drake, formalized the search in 1961 when he sat down in Greenbank, West Virginia, and wrote an equation on a blackboard before the first meeting of what would become the search for extraterrestrial intelligence. He was preparing for a small conference, 10 scientists in a room, and he wrote down the variables he thought you would need to estimate the number of communicating civilizations in the galaxy: the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually emerges, the fraction where intelligence develops, the fraction that developed technology we could detect, and the average lifespan of such a civilization. Multiply them together, and you get n, the number of civilizations we might be in contact with right now. Drake wrote the equation not to answer the question, but to organize it. He was explicit about this. He knew the values were unknown. The point was to make the unknowns visible so scientists could work toward filling them in. 64 years later, we have better numbers for the first two variables: star formation rates, planetary frequency, and almost nothing solid for the rest. The fraction of planets where life emerges is still completely unconstrained. We have one data point: Earth. A sample size of one is not a sample, it is an anecdote. The assumption underneath the Fermi paradox and underneath all 7 resolutions is that we know what we are looking for. We define civilization as something that broadcasts in radio frequencies, builds megastructures, sends self-replicating probes. We define intelligence as something that develops technology. We define life as something that runs on carbon chemistry and liquid water. Every one of those definitions is derived from exactly one example: us. The Fermi paradox is, in part, a question that presupposes its own answer. We are asking why there is no other life like us. We may not be asking whether there is life unlike us and whether we would recognize it. The physicist Freeman Dyson spent his career at the Institute for Advanced Study in Princeton, the same institution where Einstein had worked, which is worth knowing if only because it places him in a tradition of people comfortable asking questions with no near-term answers. Dyson argued in the 1960s that advanced civilizations would not broadcast at all in any way we would recognize. They would be so efficient in their energy use that they would appear thermodynamically indistinguishable from natural phenomena. They would not look like cities. They would look like warm dust clouds. We have been scanning the sky for signals that look like messages. Dyson's point was that a sufficiently advanced civilization might not send messages. It might be the medium. We have not looked for that. We have not developed the methodology to look for that. The silence may include things we are not equipped to hear. The astronomer Carl Sagan and the writer Anne Druyan spent years building the case for the search. Sagan stood in front of cameras and audiences and explained, with a patience that now reads as almost touching, why the question mattered. He died in December of 1996 in Seattle of pneumonia related to a bone marrow disorder he had been fighting for 2 years. He had spent the last months of his life still writing, still arguing for the search, still convinced that the answer was knowable if we looked long enough. He was wrong about the timeline. He was probably right about the principle. The search continues. It is better funded now than at any point in history. The instruments are more sensitive. The sky surveys are more complete. The computational tools for signal analysis are a different order of magnitude beyond what existed in Sagan's time. And the silence is the same. That is the honest position. Not that we haven't looked hard enough, though that is also true. Not that the question is unanswerable, though we have not answered it. The honest position is that we have a question formulated 75 years ago over lunch. We have 7 categories of resolution, each of which requires an unverifiable assumption. We have one candidate signal that lasted 72 seconds and never repeated, and we have the silence. Fermi's question was, where is everybody? He asked it because the math said they should be detectable. 7 decades of trying to answer it have produced only increasingly sophisticated versions of the same problem. The silence is not a mystery waiting to be solved. It is the only data we have, and we still don't know what it means.